Today, we'll understand torsion and see how structural members behave when twisting forces act along their length. Torsion occurs when a torque twists a member around its longitudinal axis, creating internal resisting stresses within the material. A simple example is a rotating shaft, where applied torque causes one end to rotate relative to the other. In structural engineering, torsion can develop in beams when loads act away from the member's center line, creating eccentric loading. When torque is applied, the member develops internal shear stresses that resist the twisting action and maintain equilibrium. For a solid circular section, torsional shear stress is highest at the outer surface and decreases toward the center. At the exact center of a solid circular shaft, torsional shear stress is zero because the radius is zero. Engineers use the relationship between torque, shear stress, and section geometry to evaluate a member's torsional strength. Torsional deformation is measured by the angle of twist, which describes how much the member rotates along its length. The angle of twist depends on torque, member length, material stiffness, and cross-sectional geometry. The shear modulus describes how strongly a material resists shear deformation when subjected to twisting forces. Cross-sectional shape also strongly influences torsional resistance, making some sections much more efficient than others. Solid circular sections resist torsion efficiently because their material is distributed continuously around the central axis. Hollow circular sections can also provide excellent torsional resistance while using less material and reducing overall structural weight. Rectangular sections behave differently because their shear stresses are distributed according to the section's shape and dimensions. Thin-walled open sections can have relatively low torsional stiffness compared with closed sections using similar material weight. Closed box sections usually perform better because their enclosed geometry allows shear forces to circulate around the section. In reinforced concrete beams, torsion becomes more complex because concrete and reinforcement work together to resist twisting. When reinforced concrete beams experience torsion, diagonal cracking can develop because the concrete experiences inclined tensile stresses. Engineers provide closed transverse reinforcement, called torsional stirrups, to resist twisting forces and control diagonal cracking. Longitudinal reinforcement also contributes to torsional resistance and must be properly anchored through the beam and its connections. Proper reinforcement detailing is essential because torsional forces must transfer continuously through the reinforcement into the supporting structure. Steel beams can also experience torsion when loads act eccentrically or connections create twisting around the beam's longitudinal axis. Engineers therefore check steel sections for torsional strength, deformation, and stability to prevent excessive twisting. Torsion rarely acts alone because structural members may simultaneously experience bending, shear, axial forces. Engineers must therefore consider the interaction between these forces, rather than checking torsion completely by itself. For example, an eccentric beam load can produce vertical bending while simultaneously causing twisting around the beams. The structure must safely resist these combined actions while maintaining adequate strength, stability under expected loading conditions. Torsional behavior matters in foundations, bridges, machine shafts, building frames, and many other engineering structures. The key concept is the internal load path, which transfers applied torque through the member toward supports. If applied torque becomes excessive, the member may experience unacceptable deformation, cracking, yielding. Engineers determine design torque, select suitable sections, and provide reinforcement or connections where required. Controlling deformation matters because excessive twisting can affect the performance of connected structural components. Understanding torsion means understanding how shear stress develops, members twist, and how different sections resist applied torque. From rotating shafts to reinforced concrete beams, every torsional system needs a reliable path to transfer twisting forces safely. So, torsion is simply a structural response to twisting, controlled by torque, material properties, and section geometry. That's why understanding torsion is essential for designing safe, efficient, and stable structures across many areas of engineering. Next, we'll explore another engineering topic and continue building our understanding of structural behavior.